Okay, those are some basic data structures and implementations, and they seem quite elementary and simple, but actually right away we can get to some very sophisticated applications of these basic concepts, and that's what we're going to consider next. Now, first thing to mention is that often the kinds of data types and data structures that we implement are found in Java libraries, and that's true in many programming environments. So, for example, stacks and queues, you can find those words mentioned in the Java libraries, and there's a Java collection library in the so-called list interface, which is displayed here. So Java has a general API for sequences of items, and it's got things like append at the end, remove from the beginning, and so forth. And it uses a resizing array, so many of the principles that we consider. There's also a linked list interface. So why not just use those? Why use our own implementations? Well, the problem is often in such library code is kind of designed by committee phenomenon that more and more operations get added. And the API becomes too broad or bloated. It's not a good idea to have lots and lots of operations in the same API. And we'll see an example in a second of the problem. The real problem is that when you do that, you can't know much about the performance, or you can't assume much about the performance. And so you can kind of immediately arrive at bad performance, even for simple clients. So our best practice that we recommend is so few of these basic data structures that we use, and they're so simple, is to go ahead and use the implementations that we've just discussed for these fundamental data structures. Maybe later on, after an experienced programmer who knows what he or she is doing could use some of these library collections effectively, but inexperienced programmers often have trouble with this. Here's a war story from student programming assignments not that long ago. So we have an assignment where you need to generate random open sites in a percolation system. We have one student who was paying attention to what we're saying and uses an array and can pick the indices into that array at random, check whether they're open, and repeat. So the array is n by n, there's n squared things, and it takes about n squared time, which is actually linear time for this application. But then we have another student who had some Java before coming to us and considered himself an expert and said, well, I'm going to use linked lists because I can use Java's library and I don't have to worry about downloading your stupid code. And so I'll just use that one and pick an index at random and delete. And that program took quadratic time. Poor Kenny, when trying to run his program for the huge instance that we asked, found that it wasn't finishing. And the reason is that the Java linked list implementation takes linear time to find an item with a given index, not constant time like an array. And that's difficult for Kenny to think about and difficult to derive that information from the implementation, so the program is just too slow. And with the Swiss knife implementation with so many operations, it's hard to know whether or not the particular set of operations that your client needs is efficiently implemented. Our insistence in this course is that students should not use a library until we've implemented it in class. At least that's some indication that you understand the performance characteristics. So now let's look at some applications then of stacks. there's stacks are really actually fundamental underlying computation because they implement recursion. And so you use stacks often every day. When you go use the back button in a web browser, the places you've been are saved on a stack. Right now, we'll look at two examples. One having to do with compiling from a programming language or interpreting into an actual computation. And then the other one is the PostScript language, which is widely used for printing and publishing. So the way that compilers implement functions is using stacks. When there's a function call, the whole local environment is pushed, and then along with the return address, and then the function return is pop the return address in the local environment. There's a stack there that contains all that information, and whether the function calls itself or not is not relevant. The stack contains the recursion. In fact, you can always use an explicit stack to make a recursive program non-recursive. So this is so when we have the GCD function computing the greatest common denominator. Greatest common denominator of P and Q is greatest common denominator of Q and P mod Q, and it just calls itself until Q gets to be 0. As this graphic indicates, it just does it by saving the information on a stack. Now, a specific example that really shows this off and also will illustrate the utility of being able to process multiple types of data with the same code is this example is Dijkstra's two-stack algorithm for arithmetic expression evaluation. So the goal is you've got an arithmetic expression. This is just actually like a simple stand-in for a program, and we'll talk about that in a second. But let's say arithmetic expressions, where you have operands and operators, and you want to evaluate it. And Dijkstra's algorithm is very simple to express. You process through the expression from left to right. If you see a value, you put it on, you can maintain two stacks, and if you see a value, you put it on the value stack, and if you see an operator, you put it on the operator stack. Left parentheses you ignore, right parenthesis you pop the operator in two values and push the result. Now that's a lot of words. Let's look at a demo. So we start out with empty value stack and operator stack, and we're going to move from left to right. So, and those are the, atop is summarized the four types of things that we could wind up with and what to do. So left parenthesis we ignore. The value we put onto the value stack, so that one goes right onto the value stack. Operator we put onto the operator stack. That plus goes in the operator stack. Left parenthesis ignore. It seems strange to be ignoring parentheses, and we'll get back to that in a second. Value, put on the value stack. Operator, put on the operator stack. It doesn't seem like we're doing much, except putting stuff on stacks. And now, when we come to a right parenthesis, that's when it gets interesting. What it says is you have the top operator and the top two values, and that's what you want to do, is apply that operator to those values and put the resulting value that you get back onto the operand stack. So we take off the top two things, we do the operation, and then we put the thing that we get onto the value stack. And that's right parenthesis. So now, continuing along, we put a star on, left parenthesis we ignore, 4 on, star, 5 goes to the value stack. Now we got a lot of stuff on the stacks, and we got 3 right parentheses, and that's going to finish up the computation. Take the top 2 items off the stack and the top operator off the operator stack, perform the operation, put the result back on the value stack. Another right parenthesis. Take the top 2 values off, perform the operation, put the value onto the value stack. And finally, the last right parenthesis. Take the 2 operators off the value stack, operands off the value stack, and operator off the operator stack, perform the operation, put the result back on the value stack. and we're at the end of the computation, and that's the result. The value of that arithmetic expression is 101. Okay? Yep. Here's the code that implements Dijkstra's two-stack algorithm. We have two different stacks. The operand stack, the operator stack is string. It could be characters, which is just our operator. Then our value stack is doubles, so that's the same stack code, but with generics. We're using two different types of data. And then simply perform Dijkstra's algorithm. If we have a left parenthesis, read a new string. If we have a left parenthesis, do nothing. If we have plus or times, push it. If we have a right parenthesis, then go ahead and pop the operator. And if it's plus, add the result of the two values at the top of the value stack. And if it's a star, multiply the two values at the top of the stack and then push the result. So, and then when you're done, then simply print out the value on the stack. And that's a fine and elegant implementation using stacks for any arithmetic expression. And it's easy to extend that to handle other types of things. So why does this work? Well, when the algorithm encounters an operator, say in the inside with, you got parenthesis, operand, operator, operand, parenthesis, it's easy to see that what it's going to do inside there is put at the top of the stack, whatever it is to put the 2 and 3 on the top of the value stack and the plus on the top of the operand stack. And then when it hits that right parenthesis, it's going to perform the operation, and it's going to proceed then exactly as if the original input were that with the value replaced. So just going from the inside out for every operation enclosed within parentheses like that, it's just repeat the argument. It's exactly as if the original expression were 1 plus 5 times 20, and then again replacing that 1 plus 100, 101. That's why Dijkstra's algorithm works. Actually, fairly easy to understand why it works. And you can go ahead and extend this algorithm to add functions like logs and sines or other operators, and have precedence among operators, have them associate multiple operations and so forth. And actually that's on the road to developing a compiler or a way to translate a program from a programming language to a computation. So Dijkstra's algorithm that uses stack is one way for entering an understanding of the basis of computation.